explains so much. And when you are looking at periodic trends, I say, when in doubt, look at effective nuclear charge. If you ever want to explain any periodic trends, this will often explain it. Okay, not always, but often it will. So let's talk about effective nuclear charge and what it means and see why it is helpful when you're looking at some of these properties. Okay. Also, I wanted to just tell you that depending on your textbook, it might be called Z, capital Z, of EFF, like subscript, effective nuclear charge. Some textbooks call it Z star. Okay, and you might wonder, why do they have this Z there? Well, this is referring to the number of protons. So, in other words, the atomic number. All right? And so, essentially, what effective nuclear charge is this is the positive charge. So, I'll just draw a little positive charge that an electron feels, and I'll put that in quotes, and we'll talk about that, from the nucleus. Okay, so we are talking about a Coulombic interaction, specifically a Coulombic attraction between a negatively charged electron and a positively charged proton in the nucleus. Okay, so it totally makes sense if you've learned about positive charges and negative charges attracting each other, that an electron would feel attracted to a nucleus. And I do realize that feeling this is this word, I always mess up this word, anthropomorphizing, you know what I mean, making a thing into a person. But you could also replace this word with detecting. Okay, so an electron is detecting a certain amount of positive charge from the nucleus, depending on which nucleus it is. Okay, and so let's use an example to see why this is an important concept to understand and the things we need to take into consideration when we are trying to figure out what is the effective nuclear charge. So let's use a smaller atom. I'm thinking maybe carbon as an example. Okay, so let's look at carbon. And let's draw essentially a cartoon picture of the atom that is showing the nucleus and then the shells of electrons around it. Okay, so I'm going to just grab a periodic table so we can remind ourselves, how many electrons are we really talking about here, and how many protons are we considering when we're looking at carbon? Okay, so carbon is element 6. So this number up here, this is our atomic number. This is the number of protons that we have in this atom. And for a neutral atom of carbon, that means we have an equal number of protons and electrons. Okay, so the structure of the atom is we've got 6 protons clustered together in the nucleus, and then we've got 6 electrons that are around it. So as I said, I'm drawing what I would call a cartoon, or it's more of the Bohr model, where we are acknowledging we've got 6 protons and they are clustered together. That's 6, right? Yeah. And yes, I realize there are neutrons there as well, but the neutrons are neutral, so they are not going to affect what we're talking about here. So I'm going to ignore them to just simplify things, okay? So here's our nucleus of the carbon atom. And then we can look back at the periodic table and we can remind ourselves, period 1, we've got 2 elements. So that means each of these elements has an additional electron. Hydrogen has 1, helium is 2. And now that first shell that holds electrons is full, and we move to the second shell. And we begin to fill electrons. 1, 2, 3, 4 electrons are in the outer shell. And we call that the valence shell. So the inner electrons are the core electrons, and they are closer to the nucleus. And we can consider them, like I said, the Bohr model shows that we have electrons that are core electrons closer to the nucleus, and then we have our next shell, and these are further away from the nucleus. Now, does the path that these electrons follow, is it a circle like we see this? Is it a solar system? No, it is not exactly. Okay, but the good news is, for the purposes of effective nuclear charge, we can look at it mostly from this point of view, which simplifies things and helps us understand the pertinent parts of what we need to know. Okay, so far for carbon, we've drawn these 2 electrons in the inner shell, and now we have those 4 remaining ones, so we can put those really anywhere we want. I'll just distribute them around, okay, on this outer shell. So this is the thing. If we look at this in this way, we can see that these electrons that are closer in, they are going to feel a stronger pull to the nucleus than these outer electrons are. And there's a couple of reasons for that. And one of them is they are simply closer. Okay? So the Coulombic attraction, it is directly proportional to the magnitude of the charge. So in other words, if you have a larger charge, that means that there's more attraction. Okay? But there's also an inverse relationship with distance. So if you have a charge that's further away, that is not going to feel the positive charge or have as much of an attraction. Okay? But moreover, there's something else happening, and that is called shielding. So if we think about these 2 electrons and we consider that they're not sitting still, okay, but rather they are taking up space in this region that's closer to the nucleus. They are essentially, you could call it or think of it as being, they're building a shield of negative electron density that's in here that is blocking how much these outer electrons can feel the positive charge. Okay? So this shielding, the net effect of this is that this electron does not feel a full +6 charge. It is blocked by these these inner electrons. One analogy that a colleague of mine used to use is a movie theater analogy, where you imagine you are sitting in a row, maybe in the middle of the theater, and if you think of the protons here in the nucleus, that's being the screen, that's the movie you're watching. Okay, so your eyes are looking and you want to see that movie, but there's a row in front of you with a whole bunch of really tall people that are blocking you. They're blocking your view. So the screen is there. You can see a lot of it. You just can't see all of it because of this shielding that's going on. Okay? So the effective nuclear charge that this proton, this is an electron. The effective nuclear charge, or in other words, the positive charge from the nucleus that this electron feels, this is going to be less than that +6 charge in the nucleus. Okay. And so let's think about carbon versus, here's carbon. Let's just go right next door and look at nitrogen and think about what will be the effective nuclear charge of this nitrogen. Now, how much are these two electrons blocking? Well, in actuality, they're not blocking it by exactly 2, but it can be very helpful if we assume that it is something like that. So we can estimate that it's around +4 that this electron can feel from the nucleus. We can say, okay, these two negative charges from these two electrons are essentially canceling out 2 of these positive charges in the center. So this electron cannot feel the full 6, and we can estimate that it's about +4. Now, if we do the same thing, this was for carbon, right? Let's do the same thing with nitrogen. Nitrogen is right next door to carbon. So now instead of 6 protons, we've got 7. Nitrogen also has 2 of these core electrons. And it also has this valence shell. But now instead of 4 of the valence electrons like carbon has, nitrogen has 5. 2, 3, 4, 5. Okay. So now let's look at the point of view of this nitrogen. Let's look at the Z effective, or effective nuclear charge, of one of these outer electrons for nitrogen. Once again, we've got the shielding going on. These core electrons are creating a shield. They are canceling out the charge of almost 2 of these positively charged protons. So this electron here is going to feel And we can say once again, less than the +7 charge from those protons, those 7 protons in the nucleus. And we're going to estimate it as being what? We've got now 7 plus 7 in the nucleus. We have these 2 core electrons, canceling out 2 of them. So we have 7 minus 2 is 5. So check it out. Between carbon, if we look at carbon, an outer electron feels +4. In nitrogen, an outer electron feels +5. These electrons feel a stronger pull towards the nucleus. That right there explains so much. I would say you would not believe it, but I know you will believe it. It explains atomic radius, trends in atomic radius across a period. It explains ionic radius as you go across a period. It explains ionization energy. Does it explain electron affinity? Electron affinity is really weird. So, I don't know about that one. It probably does to some degree, but there's variables with this one. It definitely explains electronegativity, though. So, of these 5 different periodic trends, 4 of them, when you're looking at trends across a period, like we just did here, carbon, nitrogen across a period, effective nuclear charge. Okay, so whenever you are asked to explain a periodic trend across a period, invoke effective nuclear charge.